So good morning. I'm Shin Ashiroshita, and so today, I'd like to introduce one of my work with my members. When I was in my students, and the topic is FPT algorithms, which use the curving with parameter and for the Eulerian orientation problem and ice-type models. So in this presentation, first we introduce overview of our algorithms, and then we discuss the detail of them. And to begin with, we focus on the Eulerian problems. So which is the finding the work which use every edges in exactly once. And when the beginning node and end node are same, so it is called the Eulerian circuit. So for example, we use these edges in the numbered order, so it is closed work. And it is Eulerian circuits. And the Eulerian orientation is adding the directions on each edge, so in order to contain at least one Eulerian circuit. And counting the number of Eulerian orientation has a significance in the variety of fields such as ice model or tapped polynomials. So ice model is a physics model, and which represents the hydrogen bonds on the H2Os. And in the graph meaning, each vertex corresponding to the oxygen, and edges means hydrogen bonds, and direction means plus or minus. So in the model, every vertex must contain exactly 2 integrating edges and 2 arbitrary edges. And the partition function of the ice model corresponds to the number of Eulerian orientation in this problem. And the polynomial is the two variants, two variables, polynomial which describes the graphs. And there exists the FPT algorithms for the polynomial. And in 1995, Welch pointed out that when the input is co-regular and x equals 0 and y equals -2, the cut polynomial calculates the number of Eulerian orientations for regular graph. But however, in general cases, it is known that counting Eulerian orientation is number P complete problems. And this work provides FPT algorithms which counts the Eulerian orientation for the general graphs. And FPT algorithms is the algorithms which introduce a parameter k such as tree width or branch width or curving width. And if the time complexity can be read by the multiplication of the polynomial of input size and parameter of k. And the main idea is that if the k is small, this algorithm works like the polynomial algorithm, which may be faster than compared to the exponential time algorithm. So in this presentation, we mentioned the branch width parameter and curving width parameters. This is a map of our work. We consider that input graphs, curving decomposition is already calculated by using these algorithms. And our work is that from the given curving decomposition, we can calculate this time complexity for the Eulerian orientation problems and ice-type model problems. And curving decomposition is a pair of the binary tree and the bijection between each vertex set and its leaf nodes. And in this binary tree, every edge has a width parameter. And width parameter is defined by the number of edges between the two vertex sets, which is separated by the edges. And in this example, the red edge divides the input graph into the vertex set 1, 2, and 3, 4, 5, and the number of edges between them is 4, so the width of the red edge is 4. And the width of the tree is the maximum of the all edges in the trees, and the curving width is the minimum of all possible edges and vertices pairs. So in this case, so the width parameter of the input graph is this decomposition is 4, and actually so curving width is equal to 4. So our algorithm is based on the dynamic programming on the decompositions. So the main idea is so if we divide the input graph into the some small subgraphs, so which can be easily treated compared to the whole graphs. So we use the dynamic programming keys as the in degree minus out degree of all vertices, and the value is equal to the number of orientations of the subgraphs, so which satisfy the key values. And so let me show the overview of our algorithms. So first, we fix the key of the current node which we want to calculate, and then so we fix the direction of the medieval edges, so which is the edges between the left child and the right child. And by dividing them, so the value we want to pick up from left child and right child are uniquely determined, so we can add them, multiply them, and add to the current tables. And so we all try to the medieval edges orientation, so we can calculate the current dv values. So by some analysis which we discuss later, so this algorithm works in these time complexities. So one question is that how fast this time complexity is, because coming with subparameters often becomes large, because this is because coming with is bounded by maximum degree or lower bounded by maximum degree or branch with parameters. So in order to solve this question, so we introduce the branch decomposition version algorithms to compare it. Branch width is similar to the curving width, but the difference is that we have the bisection between the edges to the leaf nodes of the tree. And in the branch decomposition, the width parameters is equal to the number of common vertices between two edge sets. And so the width of the tree or branch decomposition is defined by similarly. And in this case, our algorithm becomes this. So first we fix the dynamic table which we want to access, and then we fix the key value of the left child. So by dividing them, the right child becomes uniquely determined, and so we can add them. So by some analysis, we can this time complexity works in this contact. But however, this time complexity includes another parameter which is the maximum degree. So in this meaning, it is not FPT algorithms. And it is a comparison of the two algorithms for some input graphs. So for example, when the input is square toroidal graphs, which is one example of the four regular graphs, so our algorithm works actually faster than the branch width one. However, in the graph, the graph's maximum degree becomes large, so our algorithm requires many time complexities, or even become worst case when the input graph is starlights. And however, we know that the input, our algorithms only use one parameter. So in this meaning, our algorithm is FPT. Then I'd like to explain the algorithm for the detail of the algorithm for the Eulerian orientation. The goal of this episode is to explain why our algorithm achieves the following time complexities. So one idea is that we have to bound the number of keys, so we must calculate on each node. So one idea is that if the vertex contains too many in degree or too many out of degree, so that cannot be the subgraph of the solutions. So by our analysis, the number of keys is bounded by the product of dv plus 1. So where dv means that the number of edges between the current subgraph and the others, so which we use the vertex v. So in this graph, so the gray edges is the correspond to represents the dv edges. And so this product is bounded by 2 to the ESVS. This ESVS is mean the number of edges between the current node and the others. So this can be proved by them and finds that dv plus 1 is bounded by 2 to the dv, and summation of dv is correspond to the number of edges from S to outside. And so, because since we try all possible directions for the medieval edges, so time complexity, number of access of left child and right child is bounded by this order respectively, and so we show that this is also bounded by 2 square root 2 to the coming width. So this is because ESVS is equal to the summation of ELVS and ERVS. So LVS and RVS, the number of edges is bounded by the coming width because it is the boundary of node S, and ELVS and ELR is the edges are bound. The number of edges is bounded by the also coming width because it's a boundary of L, and similarly, and so this sum is bounded by coming width. And by summation, adding them is the one, so we can calculate the following order, and so this 3 sum is bounded by 2 square root 2 to the coming width, so we can obtain this time complexities. So then, I switch to the S-type models version problems. So the difference is that input graph is 4 regular graphs, so which means that every vertex contains exactly 4 edges. But in this problem, we have to set the different weight on each vertex for their configurations. So in this problem, we must know how many vertex of each configuration appears for each possible Eulerian orientations. So our goal is to show that this value is also calculated by FPT algorithms of curving widths. So compared to the previous case, we must store the direction of each edges. So because if in degree minus out degree, even if in degree minus out degree is same, but final configuration may become different. For example, in this case, the final configuration is different. But our strategy is that we multiply the weights of each configuration when 3 of the edges becomes directed. So which means that configuration of the corresponding vertex is fixed uniquely. So if we multiply the value, we don't have to use all directions. So instead, we only need to store the individual values out degree for them. So let me show the number of what happened in the graph. So So in this graph, so green edge means directed edges, and gray edge means the undirected edge, which is maybe the boundary on the current nodes. So our algorithm has the case for the 3 or 4 green edges, so to smaller. So the stand becomes smaller. So this is bounded by the 2 to the number of the gray edges. And summation of the gray edges is correspond to the ESVS, number of ESVS. So in this case, so number of key values is also bounded by 2 to the ESVS. So it is same as the previous case. And so we can treat them like that previous case. So by similar assumption, so we can obtain the same time complexities. And so finally, so this algorithm also runs in this time complexity. So this is summary. So we introduced 2 algorithms with exploiting the curving decomposition. One is for the Eulerian orientation problem, and the other for the type models. So there is some future works. One is how to obtain the time complexity, the curving decompositions. One is maybe one possible way is approximation for the approximation to approximation of the curving decomposition, and the other for the is to calculate, evaluate the other parameter version of this Eulerian orientation or type model problems. So we may use our framework for the different risk parameters. And the other is for the other problems, such as there is such as Ising model. So in Ising model problems, so there exists a branch with algorithms. But so there is a possibility of existing the curving with versions of algorithms, which may be used in this calculation. So our frameworks maybe works. And so thank you for listening. So is there any questions or comments? So okay.
So it's a very, very deep mathematical, right? Like, so what are the applications of this? Like, how is your limitation used? What's the?
So really, so this is very. This research is based on the very self-theoretical. So it is a bit far from the application, but so this kind of frameworks may be used to apply to the other problems. So because our algorithms, so for the Eulerian orientation is very simple, and so we can use a framework for different but similar kind of problems.
So the ice type refers to like that's like referring to ices and water ice, right? Like
yes.
So it's also applicable to other types of crystalline structures, or?
So maybe for example, if not all ice is because for regular because it has four so we can apply them to the similar kind of other it has other success, and we have other materials. So in this case, we can apply similar works or other models, for example, the 6 edges version or 8 edges version.
Okay, thanks.
So is it applicable for skin glass optimization?
Sorry.
Skin glass.
Is it in glass?
Skin glass.
Skin glass?
Skin glass, like It's also an optimization problem, like NPR optimization. So can we can discuss it? And so, like I'm working on circuit synthesis and other things. So in that case, like when the circuit become large, the number of node is very high, like we have lot of parameters to optimize. So in that case, like how can we apply this kind of, because it's very useful for optimization of large graph.
Yeah, so in this FPT framework, so inputs are input, the number of edges, the number of vertices or edges becomes large. So if so, we can obtain the possible cuts what you dividing.
So we can cut it like efficiently and find out the.
Yes.
Thank you.
Is there any other question or comment? Thank you very much.